Hello everyone and welcome to lecture number 4 of lesson Force and Pressure. Let's begin with atmospheric pressure. Air surrounds the earth from all sides. This layer of air is called atmosphere. And this atmosphere exists to about 16 km height. Also, it further extends up to about 400 km in very dilute form. The pressure created due to air is called the atmospheric pressure. Imagine that a very long hollow cylinder of unit cross-sectional area is standing on the surface of the earth and it contains air. Weight of this air is the force applied in the direction of the center of the earth. This means that atmospheric pressure is the ratio of this weight divided by the area of the surface. The air pressure at the sea level is called 1 atmosphere pressure. Air pressure decreases as one goes up in height from the sea level. Now, convergence of pressure. 1 atmosphere is equal to 101 into 10 raised to 3 Pascal, which is equal to 1 bar, equal to 10 raised to 3 millibar. And 1 millibar is nearly equal to 10 raised to 2 Pascal, which is also called as the hectopascal. Atmospheric pressure is specified in units millibar or hectopascal. The atmospheric pressure at a point in air is equal from all sides. How is this pressure created? If air exists in a closed container, the air molecules in random motion continuously hit the walls of the container. In this interaction, a force is exerted on the wall of the container and pressure is created due to this force. We constantly bear the atmospheric pressure on our heads. However, the cavities in our body are also filled with air and arteries and veins are filled with blood. Therefore, we do not get crushed under water and due to atmospheric pressure as the pressure is balanced. The Earth's atmospheric pressure decreases with height from the sea level as shown in the figure. Now, use your brain power. At the sea level, the atmospheric pressure 101 into 10 raised to 3 Pascal is acting on a tabletop of size 1 meter square. Under such a heavy pressure, why doesn't the tabletop crumble down? Atmospheric pressure is not a force, it is a pressure, meaning it acts like a force distributed over an area and acts normal to the surface of bodies. Though the atmospheric pressure at the sea level is acting on a tabletop of size 1 meter square, the tabletop doesn't crumble down as the top has an internal equalizing pressure which prevents it from collapsing. Now, buoyant force. Now let's try an activity. Take a plastic bottle and fix the lid tightly. Now place it in water and see. It will float on water. Try and push it into the water. Even when pushed, it continues to float. This experiment can also be done with a plastic hollow ball. Now fill the bottle with water to the fullest capacity and close the lid and release in water. The bottle will float inside the water. Why does this happen? The empty plastic bottle floats on the surface of water. On the contrary, the bottle full of water floats inside water but does not go to the bottom. The weight of the empty bottle is negligible as compared with the weight of the water inside. Such a bottle with water neither floats on the surface nor does it go to the bottom. This means the force due to gravity acting downwards must have been balanced by an opposing force in upward direction on the bottle filled with water. This force must have originated from the water surrounding the bottle. So, the upward force acting on the object in water or other fluid or gas is called buoyant force. I repeat, the upward force acting on the object in water or other fluid or gas is called buoyant force. Here in the picture, the arrows pointing downward is the force of gravity or gravitational force, and arrows pointing in upward direction is the buoyant force. Now, use your brain power. While pulling a bucket from a well, the bucket full of water immersed fully in water appears to weigh less than when it has been pulled out of water. Why is it so, students? This happens because when the bucket is in water, it experiences buoyant force. Therefore, we can easily pull bucket when it is in water. But once bucket is out, there is no buoyant force, and now there is only one force which is pulling bucket up, that is muscular force. Try this. Take a piece of thin aluminum sheet and dip it in water in a bucket. What do you observe? Now, shape the same piece of aluminum into a small boat and place it on the surface of water. It floats, isn't it? An iron nail sinks in water. But why does the massive steel sheet float on it? When an object is dipped in a liquid, a buoyant force acts on it, and hence it appears that the weight of the object is reduced. It becomes easier to swim in seawater than in fresh water. This is because the density of seawater is higher than the density of fresh water due to salts dissolved in the seawater. And in salty water, the buoyant force exceeds the gravitational force. Hence, buoyant force depends on two factors. First, volume of the object. The buoyant force is more if the volume of the dipping object is more. Second, density of liquid. More the density of liquid, more is the force of buoyancy. How it is decided that an object left in liquid will sink in liquid, will float on the surface, or will float inside the liquid? First, the object floats if the buoyant force is larger than its weight. Second, the object sinks if the buoyant force is smaller than its weight. And third, the object floats inside the liquid if the buoyant force is equal to its weight. So students, see in this figure, All the 3 points are clearly shown here. Next topic is Archimedes Principle. Try this activity. Take a long rubber band and cut it at one point. At one of its ends, tie a clean washed stone. Now hold the other end of the rubber band and make a mark there. Keep the stone hanging in air and measure the length of the rubber band from the stone to the mark made earlier. Now take a water in a pond and hold the rubber band at such a height that stone sinks in it. Again, measure the length of rubber band up to the mark. What is observed? This length is shorter than the earlier length. While dipping the stone in water, length of the stretched rubber gets slowly reduced and is minimum when it sinks completely. What could be the reason for a shorter length of the rubber band in water? When the stone is sunk in water, a buoyant force acts on it in the upward direction and the weight of the stone acts downwards. Therefore, the force which acts on it in the downward direction is effectively reduced. How much is the magnitude of buoyant force? Is it same for all liquids? And answer to these questions are embodied in Archimedes Principle. This principle states that when an object is partially or fully immersed in liquid, a force of buoyancy acts on it in the upward direction. This force is equal to the weight of the fluid displaced by the object. The use of Archimedes principle is very wide. This principle has been used in the construction of ships and submarines. The instruments such as lactometer, hygrometer are based on this principle. Children, here lactometer is an instrument used for determining specific gravity of milk, and hygrometer is an instrument used to measure water vapor in a space. Now, density of substance and relative density. We know that density is equal to mass upon volume. The SI unit of mass is kilogram and that of volume is meter cube. Hence, the SI unit of density is kilogram per meter cube. The property density is very useful in deciding the purity of the substance. The relative density of a substance is expressed with respect to the density of water. Relative density is equal to density of substance upon density of water. Here, relative density being a ratio of two equal physical quantities, so it has no unit. Relative density of a substance is called its specific gravity. Today's homework is: first, define atmospheric pressure and buoyant force. Second, state Archimedes principle. Third, write down the answers of Use Your Brain Power questions from textbook page number 19 in your science notebook. Fourth, write down the factors on which buoyant force depends. Thank you, children.